Got our little quiz here. No, the quiz we just did. This is quiz 25. Okay, quiz 25. And write half reactions. I guess you could write zinc solid going to zinc +2. Or you could write the zinc chloride if you wanted, but then you got to worry about the chlorides on the other side. And then the 2 electrons have to go over here. And I wrote the E0 down somewhere. Negative 0.762. Okay. And then we need half reaction for the other guy. You have Cl- and Cl2s. So I'm going to need 2 of those. And 2 negatives over here, so I have 2 negatives over there. 1.3604. Okay. So it didn't ask this, but if you wanted, this is just from the tables, if you wanted an overall reaction, or if you wanted an E0 cell, what do you got to do? If that would have been the question, it's not, but add them, but you have to do what first? Flip them. I should have, right, when I kind of wrote it down, this one out like that. I didn't know if I was supposed to flip them or not. So you got to write down the second one first, and then you flip the more negative one. So you have to flip the top one, right? So you have to flip the top one, add them up, and that's how you get your E0 cell if you wanted to, but it didn't really want it. Okay. Let's see. So B, if the battery delivers a constant, so the zinc was the answer, right, for part A. Well, right in the half reactions there, they are. There you go. You could flip the top one if you wanted to. It'd look better. If you actually did, it would look better because it's the most positive. Okay, and you're setting it up to get the overall, but it didn't ask for the overall reaction. Is everyone okay with part A? If it asked for overall, you could get it? Okay. Part B, you have 1250 amps. And I'm going to write the units for an amp. 1250 coulombs per second. 85 minutes. Right, and kilograms of chlorine. Right, I don't know if I hit. Did I hit that? I did. Wow, I don't remember doing that, John. Okay. Yeah. Okay. Kilograms of chlorine. So, we are going to need an overall reaction, aren't we? To do this, we might as well get it. Well, let's not. Hold on, I'm jumping ahead. You may not see it, so let's get it only what we need. We're going to start with the 1250 coulombs per second. Oh, let's get this guy into minutes first. How many? 85 minutes times what? 60 seconds in a minute. Okay, that's about. Thanks, 5,100. So I have 5,100 seconds. So a lot of this course in the general chemistry, converting one set of units to the other. That's how I'm so used to doing this. So really I'm converting seconds into kilograms of chlorine. And you could really start anywhere, but you're taking a chance. You might end up with 1 over what the answer you want. But I'm going to start with the 5,100 seconds and keep converting until I get kilograms of Cl2. Okay. So my first conversion factor would probably be to get it into coulombs. Because the reason I want to get it into coulombs is because I know a mole bridge from electrons into chlorine, moles of chlorine. So I got to get into electrons first. So that's where that Faraday thing comes in. 96,000, wasn't it 96,485 coulombs in a mole of electrons. Okay. Now I need, here's my mole bridge. Mole of electrons to mole of chlorine. Oh, maybe I don't need the overall reaction. I can just use that half reaction, right? Might be easier. But anyway, we'll see it. We'll get it in there. Question marks. And then I want to go from moles of chlorine into grams of chlorine. Let's see. And a mole of chlorine see, 35, it's about 70 grams or so. 70.1 maybe. Oh, then into kilograms. 1,000 grams in a kilogram. Okay, so what about our missing little ratio here? Overall reaction wouldn't help you because moles of electrons canceled in it. So let's use the half reaction. Here it is. Right? So it'll be 2 moles of electrons for every 1 mole of chlorine. 2 for every 1. And then I'll get my kilograms of chlorine. So I'm not sure how much it is, but it's a lot. Okay. So you're okay with that? Yes.
Could you explain the top part again? The zinc?
Okay, this was confusing because they had a zinc, and then they had a line and a zinc chloride, right?
Yeah.
And I bet you were doing just what I was doing. You're looking in here for zinc chloride, right? But I guess there's a couple of hints. One is that there's no chlorine on the other side. It's just zinc. So it's got to be just involving zinc. So, and the AQ, I don't know when it dawned on me, but it dawned on me, oh, they're talking about zinc plus 2. Because usually it would have been better if it would have made a real life one, like in a rechargeable battery, I'm not sure what the concentration is. Maybe it's 0.28 molar. And then if that would have been staring in front of the zinc chloride, maybe you would have realized, oh, that's zinc plus 2. His concentration is 0.28 molar, right? But the concentrations were left out. So it was a hard one to see. But it's zinc going to zinc plus 2. And he's definitely going to be the guy producing the electrons because he's the anode. Okay. He's on the left side. Remember, electrons are always going from there into there. Okay, left to right. So any other questions on the quiz? So this stuff, if you want to hang out, you can probably pick it up outside my office in an hour or so. Either that or you have to wait until Sunday if you're going to make it to our help session. Okay. So should we give this a shot? Oxidation numbers. There were some problems on that, just starting at the very beginning. What's the copper have to be? You have to remember what sulfate is. Sulfate has a what charge? -2, so the copper has to be +2. Yeah. Well, if he's +2, copper's +2. Oxygen is always what? -2. And I've got 4 of them, so I have a -8 so far. Right? So the copper's +2, the oxygen's a -2, but I have 4 of them, -8. Now you add up all the oxidation states of everything in a compound. Has to add up to be what? Well, 0 if it's neutral, right? Like in this case for phosphate, it's going to have to add up to be a -3. Right? But over here it has to add up to be the overall charge, which is 0. So a -8 and what? And a +2 would give me 0. +6. So sulfur has to be +6. Sulfur, +6. Oxygen, -2. Copper, +2. Right? Something like that. Okay. I think you got the idea, or you want to do some more of those? Miriam, you want to do some more of those? Or you want to go on? She wants to do another one. Okay, let's do the tough one. Phosphate. So, whoop. Over the oxygen, you have to write -2, but I only have 4 of them, though, Pablo. It's going to be a -8. Okay, it's a -8. So O is -2. So what does the P have to be? Has to be +5 because the overall thing has a -3 charge. Right? Okay. Just remember O is -2. Add up all the oxidation numbers, you have to get the charge. It's not so bad. And there's not very many questions like that anyway. But it's good to know. Determining oxidizing and reducing agents in a reaction. Okay, which one is... Oh, this one looks easier to figure out. If we figure him out, the bismuth one is fixed. So let's just do the manganese +2. Right? Because don't you already know what he is on that side? He's what? What's his oxidation state? +2. Yeah. So all we got to do is figure out what it is on the other side. Just figure out what it is on the other side. What is it on the other side? Manganese on the other side is what oxidation state? I hear 7? +7? Everybody agree? Yeah. Oxygen's a positive, sorry, manganese is a +7 over here. Okay, so now use the terminology. That manganese 2, it got oxidized. So manganese 2 is the, yeah. Play the game. Oh, well, that means this, I don't even know how to pronounce that. That compound has to be the oxidizing agent. You can figure it out, but there's no reason to. He has to be. Okay. How about playing around with charge, current, voltage? The quiz did that. But, oh, there's a question. Let's pick on somebody. Amanda, 1 mole of electrons contains how much charge? Yeah, 96,000. Yeah. And the unit is, everybody? Coulombs. Just coulombs. Because they just want to know the charge on 1 mole. But yeah, F is per mole, though. Galvanic cells, there's our relation. Okay, delta G is minus NF E cell. And all we're trying to get, the reason why that's there, and then these questions pop up, is that positive E's or negative E's make things, are natural, spontaneous. They're going to happen. It's positive E's because you have a negative sign in there, right? So that's why, that's where this is coming from. And that's why you can answer questions like these. Okay. So, Adrian, give me 3 reducing agents that are visible here. Yeah, so what side do you have to look at? Yeah, because reducing agents get oxidized. And this is called a table of standard reduction, right? So these guys are all getting reduced. These guys are all getting oxidized. So he's exactly right. So you want reducing agents, they got to get oxidized. So Adrian, give me, well, here he gives the hint. Adriana, give me 3 reducing agents then. 3 compounds. Okay, hang on. PB, where did you see it? Oh, she saw it right here. Okay, I'm going to mark them, otherwise we're going to have a hard time finding these guys. She said lead, PB solid, and tin solid. And no, she's just going right down the line there, and nickel solid. But she could have said anything, right? But it had to be on that, side. List the reducing agents, Miranda, that Adriana gave us. List them in order of increasing strength or reactivity. Okay, we made our little dots. Now what's the trick to doing this? These numbers don't quite correspond. We need to do what to these reactions? We need to flip them, right? We need to flip them because we want these guys, we're talking about these guys as being reducing agents. They're got to be reactants. So you got to flip them. That does what to these signs? Makes them all positive. So which one would be the most reactive? Which one would be the strongest reducing agent? It would be the nickel. All right, it has to be this one. The next one would be the tin, then the lead. That's the order of the strongest to the weakest reducing agent.
If you go further down the chart, in other words, it gets stronger.
Nickel, increasing strength. Oh, it says increasing. Oh, we're supposed to go from weakest. The weakest one was the lead. Oh, sorry. Lead, weakest, lead, and then tin, and then, oh, thank you. And then nickel. All right. Thank you, sir. Okay. How about give us 3 oxidizing agents, John? Give us 3 oxidizing agents that are visible in this table. Pb plus 2. Well, don't do the same ones. At least you're picking from the right side, though. Cobalt. Oh, I don't know. Now it's going to take forever to find this. Okay, there it is. Cobalt plus 2. And the PbSO. In the what? Okay, all right. All right, thank you, sir. Okay, so you recognize the compounds he picked. They have to be getting reduced. So he picked cobalt plus 2. There they are right there, kind of. Boom. Okay. List them in order of increasing strength. Kimberly. The weakest one first. Increasing strength. So the weakest one first. Yeah. Out of the cobalt, the lead sulfate, and the cadmium. Let's see. Oh man, are any of them really? Let's look at it in a picture sort of way. Do we do anything to these signs? No. So do they all pretty much suck as oxidizing agents? They all pretty much suck. But you can still answer the question.
So if we don't do nothing to them, then you go to the further side.
Now that means the one that's the most positive is going to be the strongest. The one that's the most negative is the weakest. They're all negative. They all suck. But some are more negative than others. You want to go from weakest to strongest. The one that's the most negative is CD, negative 0.4. Increasing strength. So you'd have cadmium. Then the PbSO4. And finally, cobalt. None of them are very good, but hey, that's how they are. That's the order that they would actually react. Does that make sense? So you could pick that out. So I could give you a whole bunch of things, and you could tell me which is the strongest, which is the weakest, right? You could even say, could this guy even be a reducing agent? Right? He's an oxidizing agent. He's getting oxidized, right? Where is he?
Yeah.
Sorry, he's getting reduced. Oxidizing agents get reduced. Oxidizing agents get reduced. Could this guy be a reducing agent? If he is, he better be where? On this side, you just gotta go look. If he's not there, it ain't gonna happen. Some compounds are on both sides, but it's rare. It's rare. Okay, so you pretty much should look just to check. In humid environments, could the following happen naturally? Jamesa. We've got an anode and a cathode reaction. Essentially, you have some iron solids stuck in some water. Could these reactions happen? Yes. You add them up. It's a positive number. See what she did? I guess, but we have to do what to one of them?
No, it's fine.
Right? Because see how the electrons? We have to flip one of these. So at first I was agreeing with Jamesa. I was thinking, I know. I just want to show you the mistake. I was looking at, right? You add these guys up. Oh, it's positive. But both Jamesa and I, we forgot to do what? Electrons got to check out the electrons. So which one are you going to flip? Oh, that electron's over there? Oh, shoot. So we're fine. We don't have to do anything. All right? What would be E0 cell? What would be E0 cell? And I didn't even see the bloody arrow. I should make it bold. He's there. He's there. So those guys, oh, you have to multiply this one through by 2, right? To get those to cancel. What's E0 cell? 0.84. You don't mess with that E0 number. The only way to change them is you flip the reaction. Okay. So it's definitely natural. It could definitely possibly happen. What's the overall reaction? Well, you pretty much just have to do what? Probably should practice it. Multiply the top one through by 2. Add up all the reactants. Add up all the products. And that's your overall reaction. I'll give you a minute to write that down there. Bigger arrows. Okay. Got it? Okay. So we have these two reactions going on. From a table of standard reduction potentials, there we go. Which metals are more reactive than iron? Therefore, may be used as a sacrificial anode reacting before the iron solid, assuming you actually slap it onto the iron pipe or whatever it is. Which metals could you use? Anna, which metals could you use? Which metals? The ones above, the ones below. Where's the one we're interested in the first place? It's right here, right? There it is, but we had to flip it. Okay. So which metals are we looking at in this table? Are they on the left-hand side of the arrow or the right-hand side of the arrow? Right-hand side, because whatever we're doing, you got to flip it. You got to flip it. Okay. So what could you flip and get you an even more positive E0 cell? Would it be the ones above or below my green arrow here? Below, right? Right? Because if you, for example, what would be one? What's that? Zinc. Zinc solid, positive 0.76. Chromium solid. Yeah, lithium. Right? Now, some of these react with water itself, so it's not going to protect the iron. So pretty much it's best to pick one up there, plus it's cheaper. Aluminum is especially really expensive. Okay, but the point is they would all work. Okay. You okay with EX3? All those will work, yep. In a beaker is dumped 0.23 molar iron 2, 2 grams iron solid, 0.45 molar manganese 2, 0.78 molar permanganate. Look at all this stuff, right? The pH is 4.5. What reaction is most likely to occur within the beaker? I could have given you more and more and more stuff. I just got tired of typing. What's the game plan for something like that? What would you do? Identify all the half reactions, right? Pick out the two that are going to give you the most positive E0 cell reaction. Look at these guys. Write out their corresponding half reactions. Because it's pure water, and this is all you have to work with. That's the power of electrochemistry. Certain things are going to happen before others, just like the zinc. That iron's not going to get touched by the water until that last microcrystal of zinc is gone. So this actually works. So identify all those half reactions. I could see there's 1, 2, I think there's only 3. See which 2 are going to be happening. Okay. Probably just write them all as reductions, and then it's easier to. All right. What I mean is just copy them all exactly as they're written in the table, and you can do the flipping later. All right, this would be the first one I would write. Right. Identify the other ones. Manganese and permanganate one. There it is. That's a long one. Oh, there it is. Cesium. Is that even in here? Oh, it is in here. All right. Okay. Did you find all three of those? I probably should have wrote that middle one down. Oh, but I got lucky. Right? That middle one, are you going to use it? You're not going to use it, right? Because first, the easiest thing is pick the most positive. Right? If you wrote them all verbatim from the table, pick the most positive. You already nailed one half reaction. Then the other one, pick the most negative. He gets flipped. So I didn't need that middle one, thank goodness. Right? So I need to flip. I might as well do it now. What did they want next? Oh, what reaction? Yeah, you got to figure out the reaction. They want to know what the reaction is, so we have to do this. So let's flip that. This is going to be Fe plus 2 plus 2 E negatives. I'm going to get rid of that middle one. I need iron solid over here. Okay. Can I just go ahead and add this stuff up now, or what do I have to do first? You see it? Oh, I had to flip it, so I got to change him to a positive. But can I just add them up? No, I got to multiply through the bottom one by 2. And then you can add them up. So I'll have Fe solid and 2 of these cesium 4s, right? And iron 2 and 2 of the cesium 3s, and about, what is that, 2.05 volts is my E0 cell. Right? Okay. So Jeff, does that make sense? That is the reaction that has to occur, and it will occur to completion before the other one even starts. Okay? Okay. Now, find the equilibrium constant. Casey, we are supposed to find the equilibrium constant, delta G0, for the proposed reaction. What was that equation that Kimberly's talking about? That equation. Okay, there's this one. Delta G0 equals negative n. Yeah. All we're doing is adding superscript zeros to the equation I give you, this one. Right? There's one. I don't see an equilibrium constant in there, though. Find the equilibrium constant delta G0. What the hell does that mean? That's not an equilibrium constant. Do you want to find the equilibrium constant or delta G0? I don't know, just pick one. find delta G0. Okay.
So are we just plugging in the
Let's plug it in.
Yeah.
We have
So
everything, right?
what's my N? 2, because it has to be the electrons that they're talking about delta G for a reaction. So this can be applied to half reactions too. If you want to apply it to a half reaction, N is the number of moles in the half reaction. But this is delta G for a reaction. So N has to be the number of electrons that cancel in the reaction. This has to be E0 cell for the overall reaction, not a half reaction. All that's for the overall reaction. So I've got a 2. I've got a 96,485. And I've got a 2.05 volts. Okay. Did they ever ask for equilibrium constant? No, they didn't. I could, though. Okay. What do you get? What are the units you put on your answer for delta G? Joules. Yeah.
Is there anything else cancel?
Yeah, well, you'd have to know that a coulomb cancels with the coulomb and the volt. The volt is a joule per coulomb. But just know Gibbs is joules and you'll be fine. Joules. Gibbs is energy. What would have asked for K? Ooh, the Nernst is the word you're supposed to be using. Use the Nernst equation to get equilibrium constants. And there's a trick to it. This is probably coming up, but E equals E0 cell, write the Nernst, minus 0.0592 all over N log, and then you do products over reactants. But at equilibrium, you have a K. And at equilibrium, what else is 0? That E. It's done. And then that's how you solve for equilibrium constants. Remember doing that? Okay. Part C, write a conventional electrochemical cell description for the proposed reaction. Okay, you Randy, I'll do part of it for you. I'll do the little double bar thinger. What? It's something. Okay. Yeah. Now remember what's supposed to go over here. The anode. And which one is that? Is that the top one or is that the bottom one? It's the top one. The only way, I don't know how I remember this. The only reason I remember this is I remember electrons are supposed to go from over here to over there. And it's supposed to tell you how to hook up the voltmeter. Red to red, black to black kind of thing. So you get positive numbers. But they're always going from here to here. So that means they're being produced over here. And she's right. The top half reaction is producing it. So how would you write that? Natalie, how would you write the cell description here? Right? Using of that half reaction. Has to be Fe solid first. Now, is there a concentration to write in front of the Fe solid? No. No, solids are solids. They don't have a concentration. Even if they would have said 2 grams, which I probably did, you don't put it there. There's no concentration for solids. Okay. Now, is there a phase change? Yes. Not always. And then it's Fe plus 2, but do you know its concentration? 0.23. So 0.23 molar Fe plus 2. Do the same thing for the other side now. Cesium-4 is 0.29 molar. And is there a phase change? No. So you're not going to put a line, we're going to put a comma. Cesium-3 is 0.35. Okay. So there's our conventional way of writing the, yes? Because it's aqueous going to aqueous. Aqueous going to aqueous. Same state. That's just their convention. Miriam, I don't know why that is. I mean, what's the big deal with lines? Commas always work. Okay. But that's not how they want you to do it. Okay. Oh, we're about out of time, right? So you've got a lot of fun things to play with on your break. Yeah, we'll meet here.